Right, good morning, everybody. I trust you're all doing well and having a wonderful day. So my name is Christo, and I'll be the moderator for this webinar. Now, I currently work with Han at Xmente, who is a pyrometallurgical consulting and systems development company. And just before I introduce Han to everybody, I'd just like to go through a couple ground rules. Just make sure that your mics are muted and video is off, just so we can save on bandwidth. We will be having a Q&A session after Han's finished with his presentation. So please post any questions you have in the Q&A section. And Han has also mentioned that he is willing to answer some questions afterwards. So if we don't get to your question or you have some very specific questions for us, please drop me a message with your contact info and your question, and we will get to it. So a quick introduction for Han. So he's a metallurgical engineer, and he's been in the pyrometallurgical industry for nearly 2 decades now. During this time, he's served various different roles in the production environment with equipment and technology, and recently also with Xmente in a consulting role. Han joined Xmente in 2018, and he's currently the lead engineer for the process team. And Han was originally from South Africa, but currently he's joining us from the Netherlands, and he's been there for the last 2 years, expanding Xmente's presence in the European metallurgical industry. And with that short introduction, Han, I'm gonna let you go, and you can give us your presentation. Thank you very much.
Yeah, thank you, Christo, and yes, good morning, everyone. Yes, it is a privilege to be able to present today. It's on a topic that we've been working on for a number of years now. In the pyrometallurgical conference earlier this year, I included a few slides on the topic, just sort of as an afterthought, and we received some feedback on that and some interest. So we decided to host this webinar to just dig a bit deeper and explore on this refractory material evaluation framework a bit more. So yeah, that's what we're going to do today. Okay, just a quick overview of the presentation. I'm just going to start by giving some context, talking about the purpose and objectives that we want to achieve with this talk. Then we'll go into the background and some reasons for change. Why would people consider switching over to new refractory materials? This is associated with a number of uncertainties, which I won't discuss in detail, but at least just list some of the main uncertainties that we've got, which leads us into the need for the framework. Then the bulk of the presentation will be on discussing the refractory material evaluation framework itself. We'll start by giving some guiding principles to give us a healthy perspective. Then I'll talk about the scope of the presentation, because refractory materials is quite a wide topic. But for this talk, just to make it more practical, we'll just focus on a narrower scope. And then the framework itself involves a number of building blocks or steps. And each of these we'll discuss, and I'll give examples just to illustrate the point. Again, the idea is not to do a complete evaluation as part of the talk, but rather just to show what the concepts are and what the building blocks are that we use for this. And then I'll just close with some key takeaways and closing remarks. Okay. So the purpose of the talk is to help support smelting operations to be profitable now and into the future. So this is again a sustainability topic. The focus here is on profitability, so economic sustainability. But obviously refractory materials does have an influence on things like your thermal efficiency. So environmental sustainability is also an issue here. But the focus now really is to help ensure that smelting operations, when they consider new refractory materials or alternative refractory materials, that they reduce risk as far as practically possible. And we'll do that by just presenting a framework for evaluating alternative refractory materials. Okay, just some of the objectives, what we want to achieve with this talk. We've spent quite a bit of time thinking about this, and we just want to share what we've learned so far. Even in preparing for this talk, I uncovered some new insights and thought about the sequence of how we do certain things. So it is an ongoing process, and we're still refining this. So this is a platform for us to share what we've learned, and then to get your feedback and your on our perspective. And there may be some key things that we are missing, and it'd be wonderful to learn about that, so that we can, as a community, we can expand on this framework and all of us use it to help us be successful. And then ultimately, we just want to get people talking. If this is a topic I think that's of interest to everyone that's attending. So yeah, just to start discussions. That's an important outcome of this presentation. Okay, just some background. I think we all know that refractory material is crucial for successful operation. I suspect no one would have joined this talk if this wasn't the case, if everyone wasn't aware of this. And we also know that the cost of failure is high. And the first cost item that we need to consider is safety. If you have an unplanned or an unexpected failure, safety of people is of serious concern. Then also the safety of equipment and refractory cost. It's hardly ever only the refractory that fails. If you have a catastrophic failure, a lot of the surrounding equipment also gets damaged. And then another cost item, which I suspect is actually a bigger cost item than the equipment and refractory cost, is that of lost production. Just thinking of the revenue loss if a furnace is off for 6 months, that can be quite a large amount of money, and that's a definite impact on profit. So what tends to happen is people tend to stick to the familiar, keep on using the refractory material that you have been using all along. It's the lowest risk, but it does come at the expense of things like improved efficiency and refractory life. There are definitely some benefits that you can gain from looking at alternative refractories, and those opportunities are lost if you just stick to what you've always done. But that's also not always possible. Situations change, and there are a number of things that one needs to consider. So one is sometimes forced to consider alternative refractory materials. And in the next few slides, I'm just going to talk about some of these aspects that we consider, or what that drives people to change and to consider alternative refractory materials. Okay, so the first one I think is probably the most obvious one, lower cost. If you've got refractory lining of say 20-25 million rand, and you've got an opportunity to buy a lining for a few million rand cheaper, that's obviously a good motivation. We know that manufacturing costs in Europe are higher than in South Africa, which in turn is higher than in Asia. So manufacturing cost comes into it, but then also the transport cost. It takes effort to get refractory materials from Asia and from Europe into South Africa, a lot more than by using a local supplier. Second one involves reliability of supply. One seriously wants to avoid interruptions in your smelting operations. And the more popular refractory suppliers tend to have a longer pipeline of orders. So if you order a refractory material now from a prominent refractory supplier, it can take a while to get the material on site, especially if you include transport time as well. And on the picture there, I think we can't ignore the fact that Austria, for example, is close to a conflict zone. That distance there is basically the distance from Bloemfontein to Cape Town. So one cannot ignore that. Don't get me wrong, I'm not trying to dissuade people from using European suppliers, but I think it is something that we need to consider, because we can't just look at the technical aspects of refractory materials. We need to think about also political issues that affected it as well. Okay, then improved refractory life. So if you have less frequent stoppages, the capital investment that you need also becomes less frequent. And similarly, the long stoppages become less frequent if your refractory life lasts long, or if refractory life is longer. I think everyone would like to have at least a couple of years of longer refractory life. It just improves your utilization and your cash flow. And then the last one I've listed, and there are probably a lot more to think about, but these are really the ones that in our discussions with producers, these are the topics that have come up and what's driving change. So the last one is energy efficiency. If we have, for example, a 30 megawatt furnace with a utilization factor of 85%, and you are able to increase its thermal efficiency from 85 to 87%, you can save along the lines of 7 million rands per year. But not only that, that's a one perspective, the energy saving, but you can also use that energy to increase your throughput. So that might be even more depending on the commodity that you work with. So there's a big opportunity to improve your design by improving your refractory lining's thermal efficiency. Okay, but that doesn't just come for free. There are a number of uncertainties, and we've grouped them. We've got two groupings of uncertainties here, and I'm not going to discuss each of them in detail, but it's just to make you aware of the things that we don't know when we start looking at alternative refractory materials. Okay, so the first group is the performance uncertainties. So the refractory material itself, when you heat it up and you put it under the conditions that it needs to be at during operation, will it be able to withstand those conditions? Then the resistance to thermostructural forces. As the refractories expand, you have compressive forces which the refractory needs to withstand, and also things like thermal cycling. Certain refractories are more prone to spalling than others. So it's an uncertainty we need. When you look at new material, how is the new material going to perform in comparison with the material that you've currently got? Then compatibility between refractories and process materials. That's not always necessary, depending on your containment concept. But it's something that one needs to know that you don't know at the start when you look at new refractory materials. Similarly, the ability to support the slag freeze lining. So all sorts of different freeze linings. People speak about conductive and insulating freeze linings, which might be somewhat relative, but it's important to understand with the conditions that the refractory material will be exposed to and the material properties, both of the material in the process and the refractory materials. Will you be able to establish and sustain the slag freeze lining? And then the ability to contain process gas, especially if you're working with sulfur-bearing materials, containing sulfur dioxide gas is sometimes a requirement. And then behavior during heat up. The refractory material undergoes changes as you heat up a furnace. So it's important to understand how well it will perform during your heat up and commissioning. Now, the second group of uncertainties are the material physical properties. And here I'm not going to discuss each of them, but we've got a number of uncertainties related to the refractory material. Things like thermal conductivity and resistance to thermal shock. Slag material properties, I think that's a big topic of discussion, something that in the last conferences we've attended, we've noticed that people are paying attention to this, but there's a lot that we still need to know regarding slag material properties, things like thermal expansion and density changes. And then feed materials as well, because the refractory materials are also in contact with solid feed material in many cases. Okay. Okay, so now going into the refractory material evaluation framework. So before I start here, I just want to give some guiding principles. I think those of you who attended the Pyrometallurgical conference earlier in the year would have seen some of these principles in Johan Zietsman's presentation, but a number of them are applicable to refractory materials as well. So I'm going to step through them to make sure that we don't have unrealistic expectations of what we actually can achieve. Okay, the first one is that perfection is a myth. You won't remove all the uncertainty. I've listed a whole number of uncertainties, and you're not going to get rid of all that uncertainty. But the idea is to remove enough uncertainty that you can proceed with confidence and know that you've done your part to make a good decision. Then failure is inevitable. If you're trying something new, you're bound to miss something important. But the point is then when you fail quickly and cheaply. We've got a whole host of tools and methods that we can use to fail quickly. We want to eliminate infeasible options as quickly as possible at the lowest cost, whether that be with a laboratory test or with a computational model. We need to make sure that we don't expend a lot of time and effort and money to investigate an option that you could have eliminated with very simple calculations. Okay, then there are no shortcuts. There is a fair bit of groundwork that one needs to do when you look at alternative refractory materials. But we can avoid detours. We don't need to do a complete battery of tests on every single refractory material that we consider. We can use simple tests to eliminate infeasible options quickly. And then lastly, we need to look at the entire life cycle. So it's not just about normal operation. We need to think about commissioning, startup, heat up, and shutdowns. Okay, so in terms of the scope of this talk, we are only looking at smelting furnaces in this case. It doesn't mean that the remainder of the talk is not applicable to other reactors, but just bear in mind that when I say something, that is my reference. So just something to keep in mind. And we're only looking at refractory bricks. Again, a lot of what we'll address is important for things like monolithic materials. But our focus now is just on refractory bricks. And then lastly, we're only looking at the technical aspect. At the end of the day, to make a decision on switching to a new refractory material, there are lots of commercial and other risk factors to consider. But we are only looking at the technical aspects. I think that's where a large part of the uncertainty lies. So that's really the focus of what we're talking about today. Okay, so a brief overview of the refractory material evaluation framework. The idea is to start doing the high-level thinking and then gradually increase the level of detail that you consider in order to enable you to make a decision ultimately. So we start off by understanding the need. We need to know what the requirements from the refractories are. What do you need it to do? Then we go a bit deeper and we start looking at the furnace itself, where the refractory materials will be used, looking at the materials, the equipment, the process, and the containment strategy. Now, as you investigate the furnace, you might find that some of your initial requirements that you identified may be incorrect or unnecessary. Just thinking, for example, about if you identify a requirement for the refractory material to be compatible with your slag, but you have a process that you are able to sustain the freeze lining, then that requirement is not necessary. So one needs to review the requirements regularly and make sure that they are realistic and help guide you in your decision making. So once you understand the furnace, you can start assessing the refractory materials. So this involves a number of physical and computational tests. So there are a number that we will address. And once you've done that, you can actually evaluate the refractory materials. So That involves taking the assessment results and comparing that with your requirements to see, does it actually meet the requirement? And then ultimately, you can act on that. Once you've got the information, you can make a decision and approve it. Okay, so we're going to start by looking at understanding the need for the refractory materials. To do this, we'll tap into systems engineering. We never did this in our undergraduate studies. So I'm just going to give some background information on systems engineering. So forgive me if this is something that everyone is familiar with, but I think it's important just to say something about systems engineering. Now, the systems engineering body of knowledge describes it as an interdisciplinary approach and means to enable the realization of successful systems. So that's quite a mouthful. But it's an approach followed by a number of big companies like Boeing, Google, NASA, and the like. And really, it's a means of helping us to deal with complexity. Now, this is a fairly rich field. I think the body of knowledge is a document of about 3,300 pages with lots of interesting methods and techniques. And we don't have to go into the detail of all of that. The systems we work with are complex, but we're not designing an aircraft. So we only need to use those tools that really help us. Okay, so let's just step back and think, okay, what is a system? Now, the definition of a system is a set of interrelated components or elements that work together to achieve a common goal or purpose. So it's basically something that can do something on its own, to put it simply. Okay, so the two tools from systems engineering that we rely on, the first one is the physical hierarchy. So that's identifying all the system elements and seeing how they fit together, how they support one another. And this is really a means of identifying all the moving parts in your system to make sure that you don't miss anything important. And the second tool is the requirement hierarchy, or maybe call it a functional hierarchy. So each component in your system or each system element has certain requirements associated with it. And these requirements also form a hierarchy with certain parent and child connections. So that's the idea with the requirement analysis, is to identify that requirement hierarchy to make sure that we address each of those requirements. Okay, so we'll start looking at the physical hierarchy. So what we do with this is to take a furnace, for example, and break it down into all its individual system elements. Then we can start thinking about each element individually and make sure to systematically step through that and that we don't miss anything important, or at least limit the likelihood of missing something important. So we'll start from the highest level, which is a system of systems. And we can consider a smelter site to be a system of systems. It contains a number of systems, such as the smelting furnace, but also others like a rotary kiln and a batching plant. And a laboratory is also considered to be a system. I'm going to expand now on the smelting furnace only, because that's where the refractory materials are located. So I'm going to unpack this gradually. So each system is can be made up of a number of subsystems. So for a smelting furnace, that could be the furnace vessel, but also the feed system, electrical system, electrodes. And there are a number of subsystems that make up the smelting furnace. Okay, the level below that we refer to as assemblies. So a furnace vessel, we have different assemblies. So the hearth, the tap walls, the different levels on the sidewall, and freeboard and the roof, they are all considered to be assemblies. And then at the lowest level, we've got our components. So each assembly is again made up of a number of components. Just looking at the hearth, we've got a wear lining and a safety lining and infill material. So the idea with the physical hierarchy is to step through the equipment that is physically present on site and identify each different part so that we can think about them on their own. Okay, so next we're moving to the second tool from systems engineering that we use, which is requirement analysis or the requirement hierarchy. And again, it's to start with the high-level thinking. I think this is something that's fairly simple to do, a requirement analysis. And I think because it's so simple, people tend not to do it. It doesn't feel like hard work. As engineers, we tend to dive into the how before we properly think about the why and what. So this is just a reminder, an encouragement to rather look at requirements before starting with detailed calculations and modeling. This is very low cost thinking, so it doesn't involve lots of modeling time and analysis. It's really a very simple means of identifying what the system needs to do. And again, it's to help us make sense of complex systems. And the format we typically do this in is just a work session, just sitting around the table and having the team think about what is required of each system element and the system as a whole, to make sure that we set realistic requirements that we can use to evaluate the refractory material in this case. Okay, so requirements are classified in a number of ways. I think I'll just show 3 common ones that we use. Now, classifying your requirements is not necessarily an objective, but we do like to think about the different types of requirements because that guides you into identifying them. So the first one we think about are the functional requirements. So, and the leading question there is, what must it do? So what must this system element do? Or what must the system do? This would be something like the furnace needs to produce X tons of ferrochrome a year. The second set of requirements are the non-functional requirements. So how must it be? So the furnace must be efficient, or it must be maintainable. And the last one is the constraints. So what is the limit? What can you not do with this system element? Or yes, what are you prevented from doing with the system element? Now we use 4 statements to think about requirements or to describe our requirements. The first one is obviously the requirement statement itself. So what is the requirement? The second one is the rationale statement. Why is this a requirement? One tends to identify requirements without always thinking about why you need it. And then we've got the performance statement. So what is it that you're going to target? And here it's important to actually quantify your performance statement as far as possible. If you're not able to quantify your performance statement, it can be an indication that it is not actually a necessary requirement. But so it's important to think about how will I quantify it, because if you can't quantify it, there's no way of checking if you actually meet the requirement. And the last one is the verification statement. How will you measure your performance? Now, just a couple of examples here. So you can see right at the top line says that's the requirement statement. So in this case, thermal losses from the half must be kept low. And the rationale for having this requirement is that losses reduce efficiency and ultimately production. You'll notice here that the performance statement, I haven't actually put a number next to it. The reason for that is that at this point, we weren't able to quantify this value. This doesn't mean that you should throw away the requirement immediately, but it does serve as a placeholder. But eventually, before you make a decision on switching to a new refractory material, your performance statements need to be quantified. Right at the bottom, we have a simple diagram. If we string all the requirements together, linking all the parent requirements to the children requirements, we end up with quite a massive diagram. So when we document our requirements, we tend to limit it just to each requirement just to its direct parents and its direct children. So in this case, for instance, the requirement with the dark border limiting half thermal losses, that is a child requirement of the requirement to be efficient. So it just helps us to think about where the requirement fits into the whole requirement hierarchy. I've got another example here, but I think I'm going to skip over that, or maybe just briefly talk about it. You'll remember from the previous slide that be efficient was a parent requirement. In this case, we're focusing on be efficient, and we're identifying all the children requirements. For example, limiting half thermal losses, limiting slag level thermal losses. So these are very simple diagrams just to help us make sense of what is actually a very complex system. Okay, so now we've gone through understanding the needs. The next one we'll look at is understanding the furnace. And there are 4 parts that we look at, or focus areas, when we try to understand the furnace. First one is the materials. There are a number of materials in a furnace, and it's from raw materials to product materials and everything in between. And there are a number of process materials that can also be present. And it's important to identify them and understand them because they do have an effect on your refractory materials. Second one is the equipment itself, the equipment that you have available and what you can and cannot do with your equipment affects your refractory materials. Then we look at the process, how you get from your feed materials to your products. And the last one is the containment concept, which is quite important to be aware of when you think about your refractory material. Okay, starting with the materials, we look at the raw materials, where they come from, what compositions they have, the typical compositions, and how variable they are. That is important to know because your refractory materials will be exposed to these materials. So understanding the ranges within which it can vary is quite important. And something we also look at is the phase behavior. Something like thermochemical calculations is quite a useful way of looking at raw materials. By simply taking the raw material assays and studying how the phase behavior changes as a function of temperature, can give us wonderful insight to show us what material your refractory material will be in contact with. And similarly, we do the same things for the products, looking at the typical composition and the variability within the products and how those products change as a function of temperature. One tends to sometimes think about the product materials at the temperature where they are tapped, but the temperature in the center of the furnace is different from the temperature right next to your refractory material. So the composition of the product materials will be different at that point. Okay, then looking at the equipment, it's really, the idea here is not to go into detailed design, but it's rather to identify those aspects that will have an influence on your refractory material. So what, how could your equipment cause things like cycling? If you think about the Soderberg electrodes, that's essentially a process within a process that places certain constraints on your operation, and that might cause you to run into issues with cycling of your refractory materials if you've got electrode breaks. So those are really the aspects that we are looking at, is to try and figure out how your equipment will affect your process. Okay, so when we look at the process itself, it's important to identify the different process zones and see what material is in contact with your refractory material at different points in the furnace. You've got different process conditions at different positions in the furnace. So it's important to understand what the local conditions are that your refractory material will be exposed to. And to a large extent, that is in comparison to your existing lining material. So it's important to understand how a new material would perform in relation to what you've currently got. Okay. Then the last component of understanding the furnace is containment. Now there are three containment strategies that at least we are aware of. The first one is that of sidewall feed heaps. By feeding large amounts of material close to the sidewall, it serves as a heat sink, and that helps to limit contact between very high temperature slag or matte and your refractory material. Okay. The second containment concept is that of slag saturation. So the idea here is to make sure or to see if your slag is saturated in the primary phase of your refractory material. This is practically what that means. We would take a slag composition and perform thermochemistry calculation, equilibrium calculations on that over a range of temperatures. And we look at the first phase to precipitate upon cooling. If, for example, your first phase to precipitate is periclase and you've got a magnesia-based refractory, the likelihood of that refractory material dissolving into the slag is much lower than if you have, for example, an alumina-based refractory material. So that is one strategy to contain the process. Okay, then the last one is to have a slag freeze lining. So by carefully controlling your mass and energy balance, you may be able to form and to sustain a freeze lining that forms a barrier between your refractory material and your slag. So that negates the need to have a compatible slag and refractory material to a large extent. Okay, so now we're going to go into the assessment of the refractory materials. There are a number of tests that we'll go into. But before I do that, I just want to remind you again of the principle, and that is when you fail cheaply and quickly. So the idea with these tests is to start with the lowest possible cost test and to eliminate infeasible material options as quickly as possible. Okay, so we start. The first step that we do in assessing refractory materials is to simply evaluate the supplier information. So the suppliers provide certain pieces of information with the refractory materials, and just based on that, one can often, on a qualitative basis, eliminate certain refractory materials as options. Okay. Secondly, we prepare assays for the refractory materials, and that allows us to study refractory thermal behavior. Then we need to prepare product assays. We need to understand what the products are inside the furnace. And once we have that, we can start looking at refractory product interaction to study slag refractory compatibility, or slag freeze lining formation. That obviously depends on your containment concept. So one wouldn't look at those two aspects if you're using the other containment concept. The next step is then to go into thermomechanical evaluation, looking at the stresses in refractory materials and the ability of the refractory materials to withstand those stresses. And then the final one is physical testing. So that is physically recreating the conditions that the refractory material will be exposed to in operation, and evaluating the performance during those tests. Okay, so when we look at the supplier information evaluation, there are two pieces of information that we can look at to assess the supplier's manufacturing details. So you can use, for example, a process description from the supplier. Now, I realize this information may not always be available, but in a perfect world, if we do have this information available, that is an important input that you can use. And also just simply visiting the supplier's site, seeing what they have available, how they do things, how they handle their materials, how they store it. And that ultimately gives you an appreciation for the factors that affect quality. Just visually inspecting what the supplier has and what they do on their site. Okay, then we also need to look at the testing details. So when you receive refractory materials, you get a data sheet with test results. The question is always how reliable are those test results? So again, one can look at the test descriptions, if that's available, look at the quality standards that are being used, and also how those test results compare to comparative tests that were done, either by the refractory supplier or by doing it yourself. And again, that gives you confidence or identify shortcomings in the test results. So to a large extent, this is a qualitative assessment. So it's a fairly low-cost assessment, no detailed calculations that you need to perform, but it is a way of quickly identifying if a supplier will be able to provide you with refractory material that is of high quality. Okay, then we need to go into refractory assay preparation. So we start off with a refractory material chemical assay and also a mineralogical assay. Both of these are important. Typically, you only get a chemical assay from the refractory suppliers, but it's easy enough to do a mineralogical assay. And based on that, you can do an assay reconciliation to make sure that your chemical and your mineralogical assay are actually in agreement. And that helps you to prepare the reconciled refractory assay, which you will use in the next step. One also needs to look at the refractory material microstructure. So using a technique like semi-EDS to identify what the different minerals are in your refractory material. So it's not enough for the bulk material to be to perform well, but the individual components also need in the individual phases also need to perform well. So if you, for example, your matrix that hold your refractory grades together, if that melts at low temperature, the refractory is not going to last. Okay, so then we look at the refractory material on its own, how it behaves as a function of temperature. So we start off with the refractory material reconciled assay that I showed on the previous slide. And on that, we can perform a thermochemical analysis and simply look at how the refractory material behaves as a function of temperature. At what point will it start to melt? And again, as I said, we also need to look at the individual phases to make sure that we don't have a phase in the refractory material that would melt prematurely. So an example of some phase distributions that we've done in the past. So on the left, we've got a magnesia refractory, and we've heated that up from 1000 to 2000 degrees Celsius. You can see for the most part, it consists primarily of a monoxide phase, so a periclase type phase. And only at the top right there, you can see a little bit of slag starting to form, but that's at a temperature in excess of 1900 degrees Celsius. So just thermally, this refractory seems to be able to withstand quite high temperatures. On the right-hand side, we've got an alumina refractory. So at 1000 degrees Celsius, it consists of mostly corundum and mullite. But as you start heating it up, you start forming some liquid slag, and that increases quite a lot as you exceed 1800 degrees Celsius. But again, the temperature that your refractory hot phase, the temperature at your refractory hot phase might not be close to your actual slag or alloy temperature. So, but this gives you at least an indication of how your refractory material will behave as a function of temperature. I'm going to skip over the next one for the sake of time. It's just another example of refractory thermal behavior. I see we are running a bit short of time, so I'm going to go through the next slides fairly quickly. But we then need to look at preparing product assays so we can look at how they will interact with the refractory materials. Okay, so again, we start off with a sample, do a chemical analysis, and end up with a product material assay. Another approach is to take your feed materials, create a reconciled assay, and perform a thermochemical analysis to estimate what your product composition would be, and then to compare that with the actual products that you get from site samples. Now, this last approach is really the only one. If you have a new plant, this is the only approach that you can follow to determine what your product material assay is, because you physically don't have product samples available. Okay, then if we look at refractory product interaction, if we've got the product materials and we know what the refractory materials look like, we can put them in contact with one another, and with thermochemistry calculations, we can look at how they are expected to interact with one another. Now, this is not a simple matter because we're not sure how much slag would be in contact with a certain mass of refractory material. So what we tend to do is we tend to scan over a range of slag to refractory masses. And at the end of the day, on this picture, on the x-axis, we've got the mass of slag as a function of as a fraction of the refractory mass. So on the far right, we've got equal amounts of refractory material in contact with a slag, for instance. So we need the refractory material to remain above that line that we indicate on this graph. Now, this is just a simple example of alumina refractory in contact with an acidic slag. So on the far left, we've only got the alumina refractory, and that is a corundum phase. And as we add slag to that material, you can see that the corundum slowly but surely changes to a spinel. And on the far right, we've got mostly spinel with some corundum. And you can see, because your solid phases are above this dotted line, it means that you end up with just as much or more solid material than you started off with in your calculation. So at least from a melting point of view, this refractory material is fine at this temperature, but you do get a phase change, which one also needs to think about if there is a volume disparity between the phases, which might cause the refractory to spoil. And then we can just increase the temperature gradually. And at this point, we can see that a significant amount of your refractory material starts to melt at this temperature. So at this point, it would not be feasible to use the material. Okay, then for slag freeze lining assessment, we can take a slag assay, perform a thermochemical analysis on it to understand how the slag changes as a function of temperature. And then with simple 1D multiphysics model, we can estimate what the likelihood is of a slag freeze lining forming, and then understand what the stresses and strains are in the refractory material. Now, for the thermomechanical evaluation, again, we can take the information that we have available at the start, the refractory material physical properties that we get from the supplier, slag physical properties and alloy mass physical properties from literature, and then create a multiphysics model to describe the process. But then you can also substantiate that by doing material property testing, taking the refractory materials and the product material samples and actually identifying or narrowing down the range of material properties to feed that into the multiphysics model again, to allow us to understand the expected stresses and strains and also the heat losses. So with a preliminary evaluation, you look at a wide range because you've got lots of uncertainty in your material properties at the start, and identify those properties that need more attention, where you need to get more certainty and narrow the ranges to look at. And then you do material property testing only on those aspects that have a large influence on the modeling results. Okay, and then finally, we can go to physical testing, where we take a product sample in contact with a refractory material at the conditions that you expect in the process and do an exposure test. And similarly, you can do an abrasion test, which involves higher flow velocities, and one can also do gas porosity tests. Again, if that is a requirement that gas containment is required in the freeboard. And at the end of the day, the absolute numbers are maybe less telling than the number compared to that of the existing material. So it's important to be able to look at the performance of an existing refractory material and compare that with a new material to see if the new material would outperform or underperform. Okay, we can then go into the evaluation of the refractory material. So now we will take these assessments and compare them, the results, with the requirements that we identified initially. So I've got a bit of a flow chart here well, actually, firstly, sorry, before I get to the flow chart, we would look at the requirements. In this case, we would look at the requirement that the refractory material solidus temperature for the new material needs to be greater than that of the existing material. So with thermochemical calculations, we can identify what the solidus temperature is and compare that with the original refractory material. Similarly, we can look at the heat losses. When we do a thermomechanical model, how does the heat losses compare between the old and the new refractory materials? And how does it meet the requirements? And again, so we need to do the evaluation after each assessment step. So we don't do the whole battery of assessment tests before we start looking at evaluation. After each test we do, we need to evaluate it against the requirements so that we can eliminate infeasible options as quickly as possible. Okay, so this is just a quick flow chart just to show how we step through the assessment and evaluation. So we take supply information and evaluate that. Is the information acceptable? Does it meet all the quality standards and is all the information provided? If it's not, you can abort. And abort here doesn't mean necessarily that you completely throw out this new refractory material, but rather that you reassess and see if there's something that you've missed or another angle that you need to look at. Okay. If the supply information is good, you can go to refractory assay preparation, do a thermal behavior assessment, and then if again you're at a point here where you need to do an evaluation, see if the refractory material is stable at the process temperature. If it's not, again you abort, but otherwise you can go on and look at the containment strategy. Do you require the material, the refractory and the product to be compatible? If not, do you require a freeze lining to be formed? And then you can do the appropriate test depending on what containment strategy you have. But before you can look at those assessments, you need to determine what your product assay is. And then ultimately, again, evaluate performance. If you require a freeze lining, is there a likelihood of a freeze lining forming? And if not, the test fails. If it is, you go on to the next step by doing a more detailed thermomechanical model and evaluating the performance. If the thermomechanical model is unsuccessful, you stop. If it's successful, you proceed to physical testing. And if physical testing is successful, you can make a decision whether or not to proceed with this refractory material. Okay, so when we make a decision on refractories, we not only need to think about the technical aspects, which is what we addressed in this talk, but we also need to look at the financial aspects, price, payment terms, exchange rates, number of commercial aspects, how long will it take to get the material, what are the quality specifications and warranties, and what risks you have, the local, regional, and international political issues may all be considerations when buying refractory material. And then we've also got social or legislative requirements, like broad-based Black economic empowerment. That is sometimes a requirement to procure a certain percentage of your materials locally. So those are all things that one needs to consider to make a decision. Okay, so just some closing remarks. There are a number of tools available for assessing refractory materials, but the answer is not in any one of those tools or in all of them, but in using the appropriate tools at the appropriate time. And again, we won't get a perfect answer, but the aim is to allow us to reduce uncertainty enough so that we can proceed with confidence. And we've been working on this for several years, but we're still gaining more insight, and we're not happy that we've arrived yet with a perfect answer. But this does give us a lot of tools to think about and reason about the process and the refractory materials and the interaction between the materials. So the idea with the framework is to help us methodically step through different tests and evaluate the performance of the refractory materials. One needs to establish good relationships with service providers. There needs to be open communication so that one it just helps you to make good decisions ultimately and gain confidence in what they can provide you. And we've got certain parts that we can do, but in certain instances, other suppliers are more in a better position to assist. But wherever we can help, we'd be happy to have discussions with people and just point you in the right direction where we can, whatever we can do to help promote discussion and help the industry make good decisions. We'd be happy to help. Okay, sorry, the last few slides were quite rushed as I realized we were running out of time, but I hope this has given you a good overview of the framework and how we can use it to think about new refractory materials. Okay.
Thank you very much for that, Han. We do have 3 questions from the audience. I'll read them to you. If it requires a bit of a longer discussion, we'll just contact them directly to give them an answer. So the first question we have is from Lloyd Nelson. I see a big focus on slag containment. Metal matte runout is usually more disastrous. What emphasis on crucible hearth and lower sidewall metal matte freeze lining control? Can a feed heap do this effectively enough? And are there any locally weak points?
Yeah, thanks, Lloyd. Yeah, that is definitely that's a big concern. Is things like matte runouts. The discussion was largely based around freeze linings, slag freeze linings, simply for the sake of time. But essentially, you need to step through that whole evaluation for each and every component in your refractory system. So recall when we look at the physical hierarchy, we went down to the component level, and we need to look at the hearth. We need to look at the skew backs and the matte level sidewall. So for each of those, we need to step through the whole process and make sure that we identify the requirements and the risks associated with each of it. So you're quite right. The idea now wasn't to look at every single material in contact with every possible product, but rather to show how we look at each component on its own.
Okay, and Han, then we've got time for one more question. It's another one from Lloyd. Everybody else, I will make a note of your questions. Just send me your contact information, then we'll respond to you directly via email. So Lloyd's second question is refractory thickness a reliable method to control heat losses? in his experience with high intensity furnaces is that regardless of the large bricks installed, it is rapidly worn to thermal equilibrium refractory thickness. So any large brick cannot be effective in sustaining heat loss.
Yeah. Yeah, this is something that we've spoken about at length with a number of our clients. People tend to gain a lot of confidence in making refractory material thicker. But at the end of the day, as you say, the furnace has the process has a natural crucible size. So it will wear away the refractories up to that natural crucible size. And I think that's a tool like multi-physics modeling is something that is quite useful for us to understand what that thermal profile would be in the furnace, and ultimately that can help guide you in your refractory design, what thickness refractory you need or what type of refractory you need in terms of its thermal conductivity and the like. So it's really about understanding the system as a whole to make sure that you're not naive in the way you're trying to contain the process and to control it.
Thank you very much, Han. Okay, that's about, I think we can answer one more question quickly. So from Priscilla, I would like to know the impact of thermal cycling on refractory materials such as alumina chrome bricks and the possibility of operating a furnace designed for continuous operations through batch operation.
Yes, the way we've looked at that in the past, and I think I'm not sure if there's a better way to look at it, but again, we use these thermomechanical models, and we've physically with the model inputs, we do cycle it. We decrease the temperature on the inside, and then ramp the temperature up again, and we see how the stresses change throughout these cycles. And that gives you a good idea at which point you would actually start to spoil off the refractories if the stresses become greater than the refractory material can actually withstand. So that's a way of looking at it. One can obviously do physical tests to do that as well, but I think in terms of looking at wide variability in process temperatures, wide fluctuations, modeling is quite a useful tool to gain insight into the resistance of refractory material to something like thermal spalling.
Thank you very much. Would somebody from SAM can we do one last question? Do we still have a little bit of time?
Yes, we can, Crystal.
All right.
Can go ahead.
Okay. Just then from Chris Anderson. Hi, Han. Thanks for sharing. Can you give us your thoughts on how this framework differs from mortars, expansion materials, and refractory design?
Sorry, Chris, I didn't get the question. It broke up a bit.
Can you give your thoughts on how this framework differs for mortars and expansion materials in refractory design?
I must admit, I haven't really thought about it all that much in terms of things like mortars. In all honesty, I would have to go and think about it a bit. I think a lot of it will be applicable. Your mortar, when it's set, does have certain material properties that one can quantify, and that would feed into perhaps models that you develop. I think the first part of the framework, just understanding the needs and understanding your furnace, I think that would be common for all refractory materials. I think when you get into the assessment details, that's where the differences come in. But I think the methods that you use to get your material properties would be quite a bit different from how you test refractory bricks. So the short answer is I don't know. But I think large parts of the framework we can still use, but we need to dig a bit deeper into things like mortars and ramming materials, because that also depends to a large extent on how it was installed, how it was applied. So there's a bit more thinking that's required in that regard.
Okay, thank you very much. That's all we have time for today. If there are any other questions, drop us an emails. You can find our information at xmente. It's .co.za, Han. Yeah.
Xmente.com.
.com. Okay.
Yes.
You can go and find us our information there. Send us an email, and then we will have a chat with you and address it. Thank you very much for everybody that attended, and Han, thank you very much for the good presentation.
Yeah, and thank you also to Simon for arranging it and giving us a platform to have these discussions and connect with one another. Yeah, I think it's wonderful. Thank you.
You're welcome.